Before the continents were touched by green life, before anything grew or moved across the land, Earth existed in a quieter and far stranger state. From space, the planet would have appeared familiar enough, a blue sphere wrapped in clouds, its oceans shimmering under sunlight. Continents rose from the water in broad shapes much like those we know today. Yet if someone could have stood upon those ancient shores, the illusion of familiarity would vanish almost immediately. The land was empty. Vast stretches of rock extended beneath open skies without a single leaf or blade of grass. Wind moved freely across barren plains, carving dust from exposed stone and carrying it across silent landscapes. Rain fell onto hard surfaces where nothing waited to drink it. Rivers cut their paths through raw terrain, flowing toward oceans that held nearly all of the planet's living inhabitants. Life in those distant ages belonged almost entirely to the sea. Beneath the rolling surface of ancient waters, the story of life was already unfolding with quiet complexity. Trilobites crept across the seafloor in slow armored procession, their segmented bodies moving through soft sediment. Primitive fish glided through dim water, guided by senses adapted to a world of currents and shadow. Strange, soft-bodied organisms drifted endlessly, carried wherever the tides chose to move them. In that underwater realm, evolution was already at work. Generation after generation, new forms appeared. Some vanished quickly, leaving only faint traces in stone. Others flourished for millions of years, shaping ecosystems that stretched across entire oceans. Yet despite this constant activity beneath the waves, the continents above remained largely untouched by life. The divide between sea and land was more than a simple boundary. It was a barrier formed by challenges that living organisms had never faced before. Water supported bodies against gravity. It carried oxygen gently across delicate tissues. It shielded creatures from the drying power of open air. On land, those protections disappeared. Gravity pressed down without relief. Sunlight struck directly against exposed surfaces. Winds pulled moisture from anything unprotected. For most living things of that ancient world, leaving the water would have meant certain death, and yet, along the margins where ocean met stone, something small and easily overlooked had begun to appear. In shallow coastal regions where waves washed gently across the shoreline, thin layers of life slowly formed across damp ground. These were not forests or even recognizable plants. They were simple organisms, primitive photosynthetic life and microbial mats, spreading quietly across surfaces that remained wet long enough to sustain them. At first they seemed fragile, almost temporary. Harsh sunlight threatened to dry them. Storms could tear them apart. The simple pull of gravity was something their ancestors had never needed to resist. Yet some of these organisms endured. They clung to rocks, trapping moisture and sediment beneath their growing layers. Year after year, tiny patches of life slowly spread along the edges of the continents. The change was so gradual that no single moment marked its beginning. But over immense stretches of time, these pioneers began altering the character of the land itself. They softened bare rock. They held moisture against the surface. They created thin films of organic material where once there had been nothing but dust and stone. For the first time in Earth's history, parts of the continents were beginning to host life. No animal yet walked across those early landscapes. No wings stirred the air. The silence remained almost complete. But the presence of these small pioneers meant something profound had already begun. The empty continents were no longer entirely empty. A subtle transformation was unfolding along the edges of the world. And although it would take millions of years before animals followed, the path they would eventually take was already being prepared. Because the great journey of life onto land did not begin with creatures crawling from the sea. It began with plants. The first great transformation of the continents did not arrive with footsteps, wings, or teeth. It began quietly, almost invisibly, with life that most modern observers might overlook. Long before animals explored the land, plants were already beginning a slow and patient invasion. At first, these pioneers looked nothing like the forests we imagine today. There were no towering trunks reaching toward the sky, no deep roots gripping the earth, no leaves rustling in wind. The earliest land plants were humble organisms, small and delicate, clinging to damp surfaces near the edges of water. Many resembled moss-like patches spreading across rock, while others formed tiny branching stems only a few centimeters tall. Yet their simplicity hid an extraordinary power. When these early plants settled along shorelines and riverbanks, they began quietly changing the character of the land itself. Before their arrival, the continents were harsh and unstable environments. Bare rock absorbed the sun's heat during the day and cooled rapidly after sunset. Rainfall rushed across exposed surfaces, carrying away minerals and leaving little behind. Nothing could easily take hold, but plants possess a remarkable talent for patience. Their bodies anchored into sediments and crevices, slowly gripping surfaces that had never supported life before. Even the smallest clusters of vegetation could trap tiny particles of dust and organic debris. Over time, these particles accumulated beneath their growing mats. This slow gathering of material created something the planet had rarely seen before. Soil. At first it was thin and fragile, little more than a damp mixture of decaying plant matter and mineral grains. Yet even this modest layer made an enormous difference. Soil held moisture after rain. It stored nutrients that plants could absorb again and again. It softened the unforgiving surface of rock. Gradually, the continents became less hostile. Where early vegetation spread, the ground remained moist longer. Shallow sediments formed along rivers and coastal flats. Small green patches appeared where once there had only been stone and dust. Each generation of plants added a little more organic matter to the growing soil beneath them. Over millions of years, this quiet process slowly reshaped the environment. The transformation was not dramatic. No single moment marked the beginning of a new world. Instead, the land changed the way dawn slowly replaces darkness, almost unnoticed until the light has already spread across the horizon. Along coastlines, the green patches thickened. Riverbanks supported broader carpets of vegetation. In some areas, tiny ecosystems formed where moisture, sediment, and plant growth worked together to create stability. For the first time in Earth's history, land began offering something it had never truly provided before: resources. These early plant communities created shelter when none had existed. They trapped nutrients that drifting organisms could feed upon. Their decaying remains produced organic material that accumulated in damp pockets of soil. To creatures living in nearby waters, the shoreline was no longer simply a dangerous boundary between environments. It had become a frontier. Within the shallow seas, countless animals lived close to these developing coastlines. Some crept along muddy bottoms, where tides carried food. Others lived among algae and sediments near river mouths. From their underwater perspective, the edge of land was slowly changing. Where waves touched the shore, green growth now waited. These patches of vegetation were more than simple plants. They represented the beginning of entirely new habitats, places where food could gather, where moisture lingered, where life might briefly survive outside the water. At first, no animal intentionally sought these places, but evolution does not always move forward through deliberate choices. Sometimes it begins with accidents. A tide retreats farther than expected. A creature finds itself stranded on damp ground. Another follows drifting food into shallower water than usual. Small encounters with the shoreline became more common, and for some animals those encounters revealed something surprising. The land was no longer completely hostile. Moist soil could support their weight. Decaying plants provided food. Thin layers of water remained trapped among vegetation. Long after waves had receded, what had once been an empty desert of stone was becoming a patchwork of opportunity. The transformation was still fragile, and the green pioneers themselves remained vulnerable to sun, wind, and drought. Yet their presence had begun altering the balance between ocean and continent. Because once plants softened the shoreline, the boundary between sea and land became something entirely new. It became a place where two worlds touched, and before long certain creatures would begin testing just how far they could move beyond the water. The animals that tried first, however, were not fish. They were something far stranger. The first animals to venture toward land did not charge forward with purpose or courage. Their journey began in a quieter way, in places where the distinction between sea and continent was already uncertain. Along ancient coastlines stretched wide tidal flats, shallow lagoons, and muddy shores where water and earth blended together in restless cycles. These environments were never stable for long. The sea arrived, the sea withdrew, and with every shifting tide the landscape transformed again. In the hours when the tide receded, broad plains of wet sediment appeared beneath the open sky. Pools of water remained trapped in shallow depressions, warming under the sun. Channels carved by retreating waves slowly drained away. For a brief time, creatures that normally lived beneath the water found themselves exposed to the air above. To most animals of that distant age, such moments were dangerous. Gills designed for water struggled in open air. Soft bodies dried quickly beneath sunlight. The shoreline was not a comfortable place to linger. Yet some creatures were better prepared than others. Among the inhabitants of these shifting coastal worlds were early arthropods, ancient relatives of the insects, spiders, and crustaceans that still inhabit the planet today. Their bodies were protected by rigid exoskeletons that formed a natural armor against the outside world. These shells provided more than protection from predators. They also slowed the loss of moisture, giving arthropods a brief advantage when exposed to dry air. Their legs offered another advantage. Unlike many marine animals that relied on fins or soft movements through water, arthropods possessed jointed limbs capable of gripping solid surfaces. These legs allowed them to crawl across sediment, climb over rocks, and navigate the uneven terrain of tidal flats. For creatures living at the edge of the sea, such abilities were often the difference between life and death. When tides withdrew, some arthropods found themselves stranded on damp ground. At first, this may have been nothing more than a desperate struggle for survival. An animal caught in retreating water would need to move quickly to reach a remaining pool before its body dried in the open air. But survival sometimes reveals unexpected possibilities. Those individuals that managed to endure brief moments outside the water encountered a world that had not yet been claimed by predators. Moist soil contained decaying plant matter. Microorganisms thrived in the thin layers of sediment created by the first land vegetation. Food was present in small but abundant quantities, and almost nothing hunted there. The oceans were crowded ecosystems filled with predators and competition. Along the shoreline, however, life remained sparse. The air above the tidal flats was quiet. The ground held resources that few creatures had learned to exploit. For animals capable of enduring short exposures to land, this environment offered something rare. Opportunity. Over many generations, the arthropods best suited for these unstable conditions slowly became more comfortable in them. Some developed behaviors that allowed them to retreat into damp crevices when water disappeared. Others became more efficient at moving across wet sediment, searching for food among patches of early plant growth. None of these creatures were planning an invasion of the continents. Evolution does not move through grand ambitions. It moves through countless small adjustments that favor survival in changing conditions. Each generation that survived a little longer outside the water passed its advantages forward. Gradually, certain arthropods began spending more time exploring the exposed shoreline before the next tide returned. Their movements left faint marks across the mud-tiny trails that washed away with the next surge of water, but hinted at something new. The boundary between ocean and land was beginning to soften. What had once been a deadly barrier was becoming a place of experimentation. Life that had evolved entirely in water was slowly discovering ways to exist beyond it, even if only briefly. These early explorers remained tied to the rhythm of tides and moisture. The oceans were still their primary home. Yet their cautious steps across mud and rock represented something profound. They were the first animals testing a new world. But crawling across wet sediment during low tide was only the beginning. Living permanently on land would demand solutions to challenges far greater than those faced along the shoreline. Because outside the protective embrace of water, gravity pressed harder, air-dried tissues quickly, and reproduction became far more difficult. If animals were ever going to escape the oceans completely, evolution would need to solve problems it had never encountered before. And those problems were enormous. For hundreds of millions of years, life had known only one kind of home. The oceans were not simply where animals lived. They were the environment that shaped every detail of their bodies. Water surrounded them from birth to death, carrying them gently through its depths and solving problems they never needed to understand. In water, Gravity was almost invisible. A creature drifting through the sea did not need strong bones or heavy muscles to support its weight. The surrounding liquid held its body up from every side. Even animals with delicate frames or soft tissues could move freely through currents without collapsing under their own mass. Breathing was simple as well. Oxygen dissolved within the water itself, passing quietly across gills that filtered it from the surrounding flow. Animals did not need to pull air into lungs or pump oxygen through complex systems. The sea delivered it directly to them. Water also protected life from another silent danger: dryness. Living tissues are fragile when exposed to open air. Without moisture, cells lose water and quickly begin to fail. But beneath the ocean's surface, this threat barely existed. Bodies remained surrounded by liquid that preserved their delicate balance. Even reproduction relied on water's gentle assistance. Many ancient animals released eggs and sperm directly into the currents, allowing them to drift and meet by chance. Fertilization occurred within the moving sea, and developing embryos remained safely suspended in its embrace. Every stage of life depended on the ocean. For creatures shaped by these conditions, the land above was not simply unfamiliar. It was hostile in ways almost impossible to overcome. The moment an aquatic animal left the water, gravity revealed its true strength. A body designed to float could suddenly collapse onto the ground. Limbs that once served only for steering or paddling were useless for lifting weight against the pull of the planet. Breathing became another immediate challenge. Gills that functioned perfectly underwater failed in open air. Without water flowing across them, their delicate structures stuck together and could no longer absorb oxygen. A creature stranded too long outside the sea would slowly suffocate even while surrounded by breathable air. The dangers did not end there. Sunlight and wind pulled moisture away from exposed tissues with relentless speed. Skin that had evolved in the constant humidity of the ocean began drying almost immediately. Without protection, dehydration could destroy cells long before an animal found its way back to the safety of water. Even reproduction posed an enormous obstacle. Eggs that developed safely underwater would shrivel in dry air. Sperm could no longer travel freely through currents. The entire process of creating new life depended on conditions that did not exist on land. To truly live beyond the sea, animals would need to solve every one of these problems. Bodies would require stronger internal structures capable of resisting gravity. Limbs would need to push against solid ground rather than glide through water. New organs would have to evolve that could pull oxygen directly from air. Skin or protective shells would need to prevent precious moisture from escaping. And perhaps most difficult of all, animals would have to invent new strategies for reproduction that allowed eggs and embryos to survive far from water. From an evolutionary perspective, this was not a small step. It meant redesigning the fundamental architecture of animal life. The oceans had spent hundreds of millions of years shaping creatures perfectly suited to an underwater world. Leaving that environment required abandoning many of those advantages and replacing them with entirely new solutions. Yet despite these overwhelming challenges, something remarkable was already beginning to happen. Along certain shorelines and shallow waters, a few creatures were slowly acquiring traits that hinted at a different future. Their bodies were still shaped by the sea, but small changes were appearing, changes that would eventually make survival beyond water possible. The land remained a harsh and unforgiving frontier, but evolution had already begun searching for ways to reach it. And among the countless animals living in ancient oceans, one particular group would prove unexpectedly capable of meeting the challenge. Among the countless creatures inhabiting the ancient oceans, one group possessed an unexpected advantage when it came to exploring life beyond the water. These were the arthropods, a vast family of animals that would eventually give rise to insects, spiders, and crustaceans. Long before these familiar forms appeared, their distant ancestors were already thriving beneath the sea. What made arthropods different was the structure of their bodies. Instead of soft skin exposed directly to the environment, they carried a protective outer shell known as an exoskeleton. This hard exterior acted like natural armor, shielding delicate internal tissues from damage and slowing the loss of moisture when exposed to air. For animals that occasionally found themselves stranded along drying shorelines, this feature provided a critical margin of survival. Their bodies also possessed another useful design. Arthropods moved using jointed limbs that could bend and grip solid surfaces. Unlike fins built for swimming, these legs were capable of lifting the body and navigating uneven terrain. Muddy flats, scattered rocks, and patches of vegetation posed far fewer challenges for a creature equipped with articulated limbs. These features had evolved for life within the oceans, yet they also happened to solve several problems associated with life on land. In coastal environments where tides constantly reshape the shoreline, certain arthropods began spending increasing amounts of time outside the water. At first, their excursions were brief. When the sea withdrew, they crawled across damp sediments searching for food or shelter until the returning tide restored their familiar world. But some of these animals discovered something unusual waiting beyond the edge of the sea. The early plants spreading across riverbanks and coastal flats were slowly accumulating organic debris. As stems died and decayed, fragments of plant material gathered within shallow soils. Microorganisms thrived among this debris, breaking it down into nutrients. For creatures capable of feeding on decaying matter, this environment offered an entirely new source of food. Among the first animals to exploit this opportunity were millipede-like arthropods. These long-bodied creatures moved slowly across damp ground, their many legs carrying them over soil and fallen vegetation. Their diets consisted largely of decomposing plant material, which they consumed and recycled back into the growing ecosystem. They were not predators, and they did not dominate their surroundings. In fact, they lived quiet and largely unnoticed lives, feeding patiently on debris that few other animals could use. Yet their modest existence marked one of the most important moments in the history of life. For the first time, animals were no longer merely visiting the land. They were living there. These early terrestrial arthropods spent their entire lives outside the water, navigating soil, vegetation, and rock, without returning to the sea that had given rise to their ancestors. The continents, which had once hosted only plants and microbial life, were beginning to support animal inhabitants as well. Their presence triggered a chain of ecological changes. As these creatures fed on decaying vegetation, they helped break down organic material into nutrients that enriched the soil. Healthier soils allowed plants to grow more densely, which in turn produced more debris for decomposers to consume. Slowly, a primitive cycle of life and decay began forming across the land. With more plant growth came more food. With more food came more animals. At first, the communities were simple. Plant matter fed the decomposers, and the decomposers quietly sustained the expanding vegetation around them. But ecosystems rarely remain simple for long. Wherever abundant food exists, predators eventually appear. It would not take many millions of years before other arthropods began evolving to hunt their relatives. New body designs would emerge: faster limbs, stronger jaws, sharper senses adapted for life above the water. The silent landscapes of the continents were beginning to awaken. Small food webs formed among patches of vegetation. Creatures crawled through soil and across fallen stems. Life on land, once nearly unimaginable, was slowly becoming a permanent feature of the planet. Yet even as these early arthropods built the first terrestrial ecosystems, a far more dramatic transformation was quietly preparing to unfold beneath the water's surface. Because along the edges of shallow rivers and swampy shorelines, certain fish were evolving traits that would eventually allow them to do something extraordinary. They would begin preparing for the journey onto land themselves. While arthropods were quietly spreading across the early soils of the continents, another story was unfolding in the waters nearby. It did not begin with bold exploration or any deliberate attempt to conquer the land. Instead, it began with a problem. Certain regions of the ancient world were difficult places for fish to live. Shallow swamps, floodplains, and stagnant lagoons stretched along the edges of rivers and coastlines. These waters were warm, often muddy, and thick with plant growth. During calm seasons, the water barely moved, and when temperatures rose, the oxygen dissolved within it began to disappear. For most fish, this was a deadly situation. Gills depend on a steady supply of oxygen, rich water flowing across their delicate surfaces. When oxygen levels drop too low, even healthy fish can slowly suffocate. In these ancient wetlands, survival demanded something more than ordinary aquatic breathing. Some fish found a solution. Over many generations, certain species developed the ability to supplement their gills with primitive air-breathing organs. These structures were not yet true lungs, but they allowed the fish to gulp air from the surface and absorb oxygen directly from it. In waters where oxygen levels fluctuated dangerously, this ability meant the difference between life and death. A fish capable of breathing air could endure conditions that others could not. But breathing was only one part of the challenge. The bottoms of these swamps and floodplains were often thick with mud and tangled vegetation. Swimming alone was sometimes not enough to move effectively through such environments. Gradually, some fish evolved stronger fins. Unlike the thin, fan-like fins used primarily for steering in open water, these new fins contained sturdy internal bones surrounded by powerful muscles. They allowed the fish to push against the muddy ground, propping their bodies upward as they moved slowly through shallow water. At first, these changes served only a simple purpose. They helped fish survive in difficult aquatic habitats. Yet evolution often produces unexpected consequences. Once these traits appeared, they opened possibilities that had never existed before. A fish capable of pushing itself upward and breathing air could briefly lift part of its body above the water's surface. This behavior might have begun as little more than necessity. When oxygen levels fell dangerously low, a fish might rise and gulp air. When a shallow pool began drying under the sun, it might struggle across mud in search of deeper water nearby. These movements were awkward and clumsy, but they were enough to keep certain individuals alive. And survival, repeated generation after generation, slowly changes a species. Over immense spans of time, the fins of these unusual fish became stronger and more flexible. Their bones began resembling the early framework of limbs. Their air-breathing organs grew more efficient, allowing them to tolerate brief exposures to the open air. Still, they remained creatures of the water. Their bodies were not yet suited for life on land. Their skin dried quickly. Their movements on solid ground were slow and vulnerable. But compared with their ancestors, they possessed abilities that hinted at a different future. They could lift themselves, they could breathe air. They could survive in environments where water itself was unreliable. The shoreline, once an impenetrable barrier for vertebrate life, was beginning to look less impossible. Meanwhile, the continents continued changing. Plants spread across riverbanks and coastal plains. Arthropods crawled through the first soils, feeding on decaying vegetation. Small ecosystems were forming where once there had been nothing but rock and wind. To the fish living in shallow wetlands, the world beyond the water was no longer completely empty. It was beginning to fill with life. The evolutionary adjustments that helped them survive dangerous waters were slowly preparing them for something far greater. Over millions of years, the line between fin and limb would blur further. Bodies designed for swimming would gradually learn how to push against solid ground. The transformation would be slow, uneven, and filled with failed experiments. But eventually, some of these strange fish would do something no vertebrate had ever done before. They would drag their bodies out of the water. The creatures that first attempted it would not look like the animals we know today. They would be awkward and vulnerable, caught between two worlds. And the land waiting for them would be unlike anything they had ever experienced. Along the edges of ancient continents, there existed places that never remained the same for very long. These were the wide, shallow regions where rivers spilled into seas, where swamps stretched across floodplains, and where muddy deltas shifted constantly beneath changing tides. In these places, the boundary between land and water was not fixed. It moved quietly, sometimes by the hour, sometimes by the season. One day a shallow basin might lie beneath calm water. Weeks later, it could become a patch of cracked mud beneath the sun. Storms flooded these landscapes without warning, while dry periods slowly drained them away again. For many aquatic creatures, such instability was deadly. Fish that relied on steady currents and stable oxygen levels struggled in these unpredictable environments. Warm temperatures could drain oxygen from the water, turning entire pools into suffocating traps. Shallow ponds could evaporate beneath the heat of the sun, leaving their inhabitants stranded in shrinking pockets of muddy water. Yet within these harsh and uncertain habitats, evolution found something unexpected. Opportunity. Some fish species developed subtle adaptations that allowed them to endure these difficult conditions better than their neighbors. They did not evolve with the intention of leaving the water. They simply evolved to survive when the water itself became unreliable. Among these adaptations was the ability to breathe air. Certain ancient fish began supplementing their gills with primitive lungs, simple organs capable of absorbing oxygen directly from the air above the surface. When oxygen levels dropped in stagnant water, these fish could rise and gulp air, giving them an advantage in environments where other fish struggled to survive. But breathing air was only part of the story. The muddy bottoms of swamps and floodplains often contained thick layers of sediment and tangled vegetation. Swimming through such environments could be difficult, especially in shallow water where fins had little room to move. Gradually, some fish evolved stronger, fleshy fins, supported by sturdy internal bones. These fins allowed them to push against the ground beneath them, lifting parts of their bodies upward as they moved slowly through the mud. The movements were clumsy compared with swimming, but they worked. A fish equipped with these muscular fins could crawl along the bottom of a shallow pool. It could push through dense aquatic plants. In extreme situations, it might even drag itself across wet sediment toward a deeper patch of water. What began as simple survival behavior slowly produced something remarkable. In certain circumstances, these fish could briefly lift themselves above the surface of the water. Their bodies, supported by muscular fins, rested against mud or submerged vegetation, while they gulped air into their primitive lungs. For a moment at a time, they existed partly outside the aquatic world. They were still fish in nearly every way. Their bodies remained shaped for swimming. Their skin was not designed to resist drying. Their movements on solid ground were awkward and inefficient. Yet they possessed abilities that none of their ancestors had ever needed. They could prop themselves up, they could breathe air, they could survive in environments where water itself was unpredictable. Within the unstable wetlands of the ancient world, these unusual fish lived in conditions that constantly tested their limits. Floods, droughts, and shifting shorelines forced them to adapt to changing landscapes where land and water blended together. These places became natural laboratories for evolution. Generation after generation, small advantages accumulated. Fish that could tolerate low oxygen survived longer. Those capable of pushing through mud escaped drying pools. Individuals that could gulp air endured conditions that killed others. None of these traits were originally meant to allow life on land, but together they formed a set of abilities that made something extraordinary possible. Within these shallow wetlands, evolution had unknowingly created creatures capable of existing in two worlds at once. They were no longer fully creatures of open water. Yet they were not truly land animals either. They lived in the narrow space between environments, moving cautiously through muddy shallows where ancient rivers met the continents. And somewhere among these strange fish, one lineage would eventually reveal what that transition truly looked like. When its fossils were finally discovered hundreds of millions of years later, they would transform our understanding of how vertebrate life first approached the land. In the early years of the 21st century, a team of paleontologists traveled to one of the most remote places on Earth. Their destination was the frozen landscape of the Canadian Arctic, a region where the ground remains locked beneath ice for much of the year. At first glance, it seemed like an unlikely place to search for clues about ancient life. Yet the rocks exposed there held a secret buried for nearly 400 million years. The scientists were searching for fossils from a very specific moment in Earth's history, the time when vertebrate animals were beginning to explore the edges of land. Most fossils from that distant era had already revealed fragments of the story. Some belonged clearly to fish, others belonged to early land animals, but the transition between them remained mysterious. Somewhere in the ancient past, fish had slowly transformed into creatures capable of crawling onto land. Yet the fossils showing exactly how that change occurred were frustratingly rare. In 2004, after weeks of careful excavation among the exposed rock layers of the Arctic islands, the researchers uncovered something extraordinary. Embedded within the stone was the skeleton of a creature that looked both familiar and impossible at the same time. They later named it Tiktaalik, a word drawn from the language of the Inuit people who live in the region. It referred to a type of large fish that lives in shallow waters, an appropriate name for an animal that had once inhabited ancient river deltas and swampy floodplains. At first glance, Tiktaalik appeared to be nothing more than a fish. Its body was covered in scales. It possessed fins rather than true limbs. Its skull held structures consistent with gills that allowed it to breathe underwater. In many ways, it seemed like just another member of the ancient aquatic world. But when the scientists studied its skeleton more closely, they began noticing details that did not belong to ordinary fish. Inside its front fins were bones arranged in a surprisingly familiar pattern. Instead of thin fin rays alone, the internal structure included bones similar to those found in the arms of land animals. There was a single bone connected to two smaller bones beyond it, followed by a cluster of elements resembling early wrist joints. The resemblance was unmistakable. Tiktaalik's fins contained the beginnings of a limb. Another feature revealed an equally strange adaptation. Most fish have skulls fused directly to their shoulders, which means their heads cannot move independently from their bodies. But Tiktaalik possessed something unusual, a flexible neck. Its head could pivot and lift separately from the rest of its body, an ability far more useful for animals navigating shallow environments or raising their heads above water. Even its ribcage hinted at a life that was not entirely aquatic. The ribs were thicker and stronger than those of typical fish, suggesting that they helped support the animal's body against gravity when it rested on the bottom or lifted itself partially above the water. Taken together, these features painted a remarkable picture. Tiktaalik was not simply a fish, but it was not fully a land animal either. It likely spent much of its life in shallow rivers and swamps, propping itself up with its limb, like fins as it moved across muddy bottoms or through dense vegetation. At times, it may have raised its head above the water's surface, breathing air in oxygen-poor environments, much like some ancient fish already did. Its movements on land, if they occurred at all, would have been slow and awkward. Yet the structure of its body revealed something profound. Within the anatomy of this strange creature existed the early blueprint for the limbs that would eventually carry vertebrates across the continents. For the first time, scientists had discovered a fossil that clearly stood between two worlds. Tiktaalik was a bridge between fish and land animals, a living experiment from a time when evolution was testing new ways for vertebrates to interact with the environment beyond the water. Its discovery confirmed something astonishing. The first steps onto land had not appeared suddenly with fully formed animals. They had been quietly developing within fish themselves, hidden in their fins and bones long before the first true footsteps touched the ground. Yet even Tiktaalik was only part of the story, because eventually some vertebrates would take the next step. They would leave the water behind completely. For countless generations, the boundary between water and land had been tested, but never fully crossed by animals with backbones. Fish had lingered in shallow wetlands, propping themselves against mud and vegetation. Creatures like Tiktaalik had shown that fins could begin to resemble limbs. Yet even these strange animals still belonged primarily to the water. Then, slowly, evolution took the next step. Over millions of years, certain lineages of these transitional fish continued changing. Their fins became stronger and more flexible, gradually transforming into true limbs capable of supporting weight. Bones within these structures lengthened and formed joints that allowed the limbs to bend with greater control. Eventually, some of these creatures developed something even more remarkable: digits. Instead of fins ending in rays suited only for swimming, their limbs terminated in primitive fingers and toes that could press against solid surfaces. These digits allowed them to grip mud, push against riverbanks, and lift their bodies in ways earlier fish never could. Their skeletons also evolved to handle a new challenge: gravity within the water. Buoyancy had once carried their bodies effortlessly. On land, that support vanished. To survive even briefly outside the water, these animals needed stronger bones and sturdier rib cages capable of holding their organs in place. Lungs, once simple air-breathing organs used during oxygen shortages, became more efficient. These creatures could now inhale air and extract oxygen without relying entirely on water flowing across gills. Taken together, these changes produced something the Earth had never seen before: the first vertebrates capable of living partly on land. These early pioneers resembled what we now recognize as primitive amphibians. Their bodies still carried many features of their aquatic ancestors, yet their limbs allowed them to crawl across muddy ground, navigate vegetation along riverbanks, and explore environments that had once been inaccessible. Their movements were not graceful. Compared with modern animals, they likely dragged themselves awkwardly across wet surfaces, pausing frequently as their bodies adjusted to gravity. Yet even these clumsy motions represented an extraordinary transformation. For the first time in Earth's history, animals with backbones were walking on land. Still, the continents remained a difficult place for them. Their skin required moisture to remain healthy, meaning they could not wander far from wetlands or rivers. If their bodies dried out beneath the sun, survival quickly became impossible. Their reproduction remained tied to water as well. Their eggs, lacking protective shells, had to be laid in aquatic environments where developing embryos would not dehydrate. Because of these limitations, the earliest amphibians lived lives balanced carefully between two worlds. They hunted along riverbanks and swampy forests, feeding on small arthropods that already inhabited the land. Yet when the time came to reproduce, they returned to the safety of water where their eggs could develop. For them, the continents were not yet a permanent home. They were a new territory, one that evolution was only beginning to explore. Even with these restrictions, their presence changed the character of the land forever. Until that moment, terrestrial ecosystems had been dominated by plants and small invertebrates. Arthropods crawled through soil and vegetation, largely free from large predators with complex skeletons. Now something new had arrived. Animals capable of hunting, moving with strength, and interacting with the land in ways no creature had before. The quiet continents that once hosted only scattered life were beginning to grow more dynamic. Food chains expanded. Predators and prey began shaping each other through evolutionary pressure. Environments that had once seemed empty and silent slowly filled with movement. Life on land was becoming more complex, and with complexity comes rapid change. The arrival of amphibians marked only the beginning of a transformation that would reshape the entire planet. Over the following millions of years, plants would grow larger and taller, creating the first true forests. Arthropods would evolve into forms far larger than those seen today. Entire ecosystems would develop across wetlands and plains. The world was preparing for an explosion of life. Yet these early amphibians were only the first chapter of that story. Soon the continents would transform into landscapes filled with towering vegetation, enormous insects drifting through humid air, and creatures unlike anything alive today. As animals cautiously explored the damp edges of land, the plants that had first softened the continents were quietly transforming into something far greater. For millions of years, those early pioneers had remained small, spreading across soil in low green carpets that clung close to the ground. Their fragile stems and leaves were well suited for the harsh environment they first encountered. But evolution rarely remained still. Gradually, some plants began growing taller. The change was subtle at first. Certain species developed stronger internal structures that allowed them to lift their bodies slightly higher above the ground. With height came advantages. Taller plants could reach more sunlight and spread their spores farther across the landscape. Over time, this simple competition for light began pushing plants upward. Generation after generation, stems thickened and strengthened. New tissues evolved that could carry water from roots buried in soil to leaves exposed to the air. These internal channels allowed plants to grow far larger than their ancestors ever could. Eventually, the continents witnessed something entirely new: trees. Among the earliest of these towering plants was a remarkable species known today as Archaeopteris. Though distant from modern trees in many ways, it possessed a structure surprisingly familiar to our eyes. A thick trunk rose upward from the soil, supporting branching limbs that spread outward in wide patterns. Above the ground, leaves gathered sunlight in broad clusters. For the first time in Earth's history, the land was no longer dominated by low vegetation. Vast forests began spreading across river valleys and wetlands. These ancient forests were very different from those we know today. The air was warm and humid. Rivers moved slowly through thick layers of sediment and plant debris. Giant tree-like plants stood in dense formations, their roots reaching deep into the soil and anchoring the land in ways that had never happened before. The roots of these early forests transformed the continents. Before trees appeared, rainfall easily washed loose sediment away. Rivers wandered freely across landscapes, carrying soil back toward the sea. but the expanding root systems of forest plants held the ground firmly in place. Soil layers thickened and stabilized, allowing even more vegetation to flourish. The fallen remains of plants added another important change. Leaves, branches, and trunks eventually died and accumulated on the forest floor. Over time, these decaying materials formed thick layers of organic matter that enriched the soil beneath them. Nutrients once scattered across bare rock were now stored within the growing ecosystems of the land. These forests did not simply reshape the ground. They also began reshaping the atmosphere itself. Through the quiet process of photosynthesis, plants absorbed carbon dioxide from the air and released oxygen as a byproduct. With forests spreading across vast regions of the continents, this exchange began altering the chemical balance of the planet's atmosphere. Slowly, oxygen levels increased. The change was gradual, unfolding over millions of years. Yet the consequences were enormous. As oxygen accumulated, the air itself became richer and more supportive of animal life. Land was no longer just a difficult frontier waiting to be explored. It was becoming a thriving biological world. Across the expanding forests, new habitats appeared everywhere. The shade beneath towering plants created cool, damp environments. Thick layers of fallen vegetation formed shelter and food for countless small organisms. Rivers and wetlands winding through these forests offered stable environments for creatures transitioning between water and land. Life responded quickly. Arthropods crawled through the deepening soil. Early amphibians hunted along the edges of swamps. Ecosystems that once consisted of only scattered patches of vegetation began growing into complex webs of living relationships. The continents were no longer silent. They were becoming alive with movement. And yet, these forests were still only the beginning of something far stranger. The rising oxygen levels, the abundant plant growth, and the expanding habitats were setting the stage for creatures that would seem almost unbelievable today. Because within these ancient forests, evolution was preparing to produce animals that modern ecosystems rarely create, creatures that would grow larger than anything their kind has ever become again. As the first forests spread across the continents, the atmosphere of the planet began to change in a quiet but powerful way. Plants were removing carbon dioxide from the air and releasing oxygen in its place. Over millions of years, this gradual exchange began enriching the atmosphere far beyond the levels we experience today. During parts of this ancient era, oxygen concentrations rose dramatically. To modern eyes, the difference might seem small. Today, the air contains a little over 20% oxygen, but during the height of these early forests, oxygen levels climbed much higher. The atmosphere became thick with the gas that fuels animal metabolism. This invisible shift had extraordinary consequences. Among the creatures living within these forests were arthropods, descendants of the same pioneers that had first crawled across damp soils millions of years earlier. Their bodies relied on a simple respiratory system made of tiny tubes that delivered oxygen directly through their exoskeletons to internal tissues. In the modern world, this system limits how large arthropods can grow. But in an atmosphere rich with oxygen, those limits expanded dramatically. The forests began filling with giants. Some of the most striking inhabitants of this world were enormous dragonfly-like insects known today as meganeura. Their wings stretched nearly 70 centimeters from tip to tip, making them larger than many modern birds of prey. They drifted through the humid air above forest canopies, their long wings beating slowly as they hunted smaller insects below. To imagine standing beneath those ancient trees is to picture shadows gliding across the sky, silent hunters with wings as wide as a hawk's. On the forest floor, other giants moved through the thick layers of fallen leaves. Millipede-like creatures stretched more than 2 meters in length, their segmented bodies rippling as hundreds of legs carried them slowly across the damp ground. These enormous arthropods fed on decaying plant material, helping recycle nutrients back into the soil just as their smaller ancestors once had. But not all of the forest's inhabitants were peaceful decomposers. Hidden among tangled roots and fallen branches were predatory arthropods equipped with powerful pincers and venomous stings. Some resembled enormous scorpions or centipedes, moving quietly through the shadows as they searched for prey. To the creatures living within those forests, these predators must have seemed terrifying. Yet they were not monstrous accidents of evolution. Their size was a direct consequence of the atmosphere surrounding them. With abundant oxygen flowing through their respiratory systems, arthropods could sustain bodies far larger than those possible in the modern world. The forests themselves provided the perfect environment for such creatures. Thick vegetation trapped humidity, preventing delicate exoskeletons from drying. Fallen plant matter supplied endless food for decomposers. Small insects filled the air and soil, providing prey for larger hunters. These ecosystems were vibrant and complex. But the giants of the arthropod world were not the only animals living there. Among the rivers, swamps, and wetlands threading through these forests lived the descendants of the first vertebrates that had crawled onto land. Early amphibians moved cautiously through the undergrowth, hunting insects and other small animals near the water's edge. Compared with the towering insects and sprawling millipedes, these amphibians were still modest in size. Yet their presence represented something important. For the first time, vertebrate predators were sharing the land with arthropods. This coexistence began shaping new evolutionary pressures. Amphibians fed on insects and smaller arthropods, while larger arthropod predators competed with them for food. Each group gradually adapted to survive alongside the other. The forests had become a stage for a new ecological balance. Giant insects ruled the air and soil, while early vertebrates cautiously expanded their presence along the ground and water. For millions of years this strange world thrived, humid forests filled with towering plants and creatures that would appear almost mythical today. Yet even these extraordinary ecosystems were only a temporary chapter in the story of life, because evolution was quietly preparing another transformation, one that would finally free vertebrate animals from their ancient dependence on water. The amphibians that wandered through the ancient forests had accomplished something extraordinary. Their ancestors had emerged from water and learned to move across land with limbs that could support their bodies. They hunted insects among fallen leaves and rested in the shade of towering plants. In many ways, they seemed well adapted to this new world. Yet a quiet limitation held them back. Despite their ability to walk across land, amphibians still depended on water for the most important part of their lives. When the time came to reproduce, they returned to rivers, swamps, or shallow pools. Their eggs were soft and fragile, lacking protection against dryness. Without constant moisture, those eggs would quickly fail. This meant amphibians could never truly leave the water behind. Their lives remained tied to wetlands and riverbanks, places where the next generation could survive. The forests might stretch far beyond these areas, but amphibians could only explore the edges. The interior of the continents remained mostly beyond their reach. For millions of years, this limitation shaped the boundaries of vertebrate life on land. But evolution rarely leaves such barriers unchallenged. At some point in the distant past, a new solution appeared within a small group of vertebrates. It did not involve stronger limbs or sharper teeth. Instead, it appeared within something far more delicate. The egg in amphibians. Eggs developed directly in water. But in these new animals, the egg itself began changing in remarkable ways. Layers of protective membranes formed around the developing embryo. These membranes created a small internal environment filled with fluid, allowing the embryo to grow safely even outside water. This structure became known as the amniotic egg. Inside the egg, the embryo was surrounded by liquid that prevented it from drying. Other membranes handled the exchange of gases and stored waste products. Nutrients packed within the egg provided the energy needed for development until the young animal was ready to hatch. For the first time, a vertebrate embryo could develop entirely on land. No river was required. No swamp or shallow pool was necessary. The egg itself carried everything the developing life needed. This simple yet profound change removed one of the last barriers preventing vertebrates from spreading fully across the continents. Animals that possessed this new reproductive strategy were no longer restricted to damp environments. They could venture into dry forests where amphibians could not survive. They could move across plains far from rivers. Some would even adapt to deserts where water was scarce. These animals were the earliest reptiles. Their bodies still resembled those of their amphibian relatives in many ways, but the amniotic egg gave them a freedom no previous vertebrate had known. They could live their entire lives away from open water. It is difficult to overstate the significance of this innovation. With one evolutionary breakthrough, the geography of life changed. The continents were no longer divided into narrow strips of habitable land near water. Vast new environments suddenly became available to animals with backbones. Forests far from wetlands could now support vertebrate populations. Rocky hills and dry plains became part of the living world. Ecosystems that once held only plants and arthropods began filling with reptiles exploring their surroundings. And from those early reptiles, an astonishing variety of life would eventually emerge. Some lineages would grow into the giant dinosaurs that later dominated the planet. Others would evolve into birds that filled the skies. Still, others would give rise to mammals, including the distant ancestors of humans. All of those stories trace their origins to this single evolutionary invention, a protected egg capable of carrying life beyond the water. At the moment this adaptation appeared, vertebrate animals were finally free to leave the ancient constraints of the oceans and wetlands behind. The continents, once silent and empty, were now open to exploration. And with that freedom, the history of life on land was about to accelerate, because with the amniotic egg came the rise of creatures that would reshape the planet in ways no one could have imagined. The next chapter of Earth's story would belong to reptiles, and eventually to giants. For millions of years, amphibians had lived along the shifting boundary between water and land. They crawled through dense vegetation, hunted among fallen leaves, and rested in the shade of towering plants that filled the ancient forests. Their limbs allowed them to move across soil and mud with surprising confidence. Yet no matter how far they wandered, their lives always returned to the water. When the time came to reproduce, they slipped back into swamps, rivers, or quiet pools. Their eggs, soft and vulnerable, could not survive the dryness of open air. Without moisture, the next generation would never begin. This invisible tether kept amphibians tied to wetlands and riverbanks. They had learned to walk on land, but they could not truly live there. Still, evolution does not rest when challenges remain. Across the vast stretches of the Carboniferous world, subtle changes were unfolding within certain lineages of vertebrates. These changes were not dramatic at first. They appeared gradually, generation after generation, as small adjustments to bodies already adapted for life near the water. One of those adjustments involved the skin. Amphibian skin remains thin and moist, allowing gases and water to pass easily through it. This feature works well in humid environments but becomes dangerous in dry conditions. In contrast, the bodies of early reptiles began developing thicker, more protective skin that resisted the loss of moisture. This simple barrier allowed them to survive longer in dry air. Another change occurred within their skeletons. As reptiles evolved, their bones strengthened, and their bodies became better suited for life away from the buoyancy of water. Their limbs carried them more efficiently across solid ground, allowing them to explore environments farther from the wetlands, where amphibians remained most comfortable. But the most important transformation was still hidden within something small and easily overlooked: the egg. As the amniotic egg appeared within these early reptiles, reproduction itself changed. Instead of laying fragile eggs in water, reptiles produced eggs surrounded by protective membranes and a durable outer covering. Inside, the developing embryo remained surrounded by fluid, nourished and protected as it grew. For the first time, vertebrate young could develop entirely on land. With this innovation, the ancient dependence on water quietly disappeared. The impact of this change spread across the continents. Animals with backbones were no longer confined to the narrow strips of land near rivers and swamps. They could move through dry forests, cross rocky landscapes, and inhabit areas where water was scarce. The continents, once quiet and sparsely populated, began filling with new forms of life. Yet the reptiles that first carried this transformation forward were not the fearsome creatures people often imagine when they hear the word reptile. They did not resemble dinosaurs or giant lizards. They were small animals, cautious and adaptable, moving quietly through the shadows of the ancient forests. Their bodies were modest in size, often no larger than modern lizards. They hunted insects and small prey among the roots of plants and across the forest floor. Many likely lived hidden lives beneath fallen branches or within shallow burrows. But within their biology existed a revolutionary advantage. They could live their entire lives without returning to water. This freedom allowed reptiles to explore territories that had remained inaccessible to amphibians. Dry uplands, scattered plains, and forest interiors gradually became part of their world. Each new generation spread a little farther, adapting to environments that had once been beyond reach. Life on land was entering a new phase. The presence of reptiles added new layers of complexity to ecosystems already shaped by plants, insects, and amphibians. Predators and prey evolved alongside one another. Habitats expanded into regions that had once been nearly empty. What began with small pioneers was quietly reshaping the entire planet. The reptiles themselves did not know it, but they carried within their lineage the potential for creatures that would one day dominate the earth. Dinosaurs, birds, and even mammals would trace their ancestry back to these humble beginnings. Yet for now, the first reptiles were simply explorers stepping cautiously into landscapes that were still unfamiliar. Once reptiles gained independence from water, the structure of life on land began changing rapidly, and the world they were entering was unlike anything alive today. There was a time in Earth's distant past when the air itself was different. It looked invisible, just as it does today, but its hidden composition carried a remarkable power. During the Carboniferous period, the atmosphere contained far more oxygen than modern life has ever known. In some regions, the concentration may have approached 35%, a level that would feel strangely rich to the lungs of any creature alive. Now, this change had been building slowly for millions of years. The vast forests that spread across the continents were responsible. Towering plants captured carbon dioxide from the air and locked much of that carbon deep within growing trunks, roots, and buried plant material. With carbon removed, oxygen steadily accumulated in the atmosphere. The forests breathed, and the planet changed with them. At first the consequences were subtle. Plants flourished in the warm, humid climate. Wetlands expanded across broad equatorial regions. Rivers drifted slowly through endless swamps where dense vegetation trapped moisture and heat. But the rising oxygen had another effect. It allowed animals to grow far larger than they otherwise could. Among the creatures most affected by this atmospheric richness were the arthropods. Unlike vertebrates, arthropods do not rely on lungs to circulate oxygen through their bodies. Instead, air travels through a network of tiny tubes that carry oxygen directly to their tissues. This system works efficiently for smaller bodies, but under modern oxygen levels, it places limits on how large these animals can become. In a world filled with extra oxygen, those limits expanded dramatically. The forests became home to giants. Above the canopy, enormous dragonfly-like insects glided through the thick air. One of the most famous of these creatures, known today as Meganeura, possessed wings stretching nearly 70 centimeters across. Their wings beat slowly as they drifted over rivers and swamps, hunting smaller insects below. To anyone standing in those forests, the sight would have been astonishing. A shadow would pass overhead, silent except for the faint rustle of massive wings slicing through humid air. Closer to the ground, the forest floor moved with life as well. Among the tangled roots and fallen leaves crawled enormous millipedes, whose bodies stretched more than 2 meters in length. Their long segments rippled like living chains as hundreds of legs carried them slowly across the soil. These creatures fed on decaying plant matter, breaking down fallen vegetation that accumulated in thick layers beneath the trees. Hidden among the shadows were predators equally impressive. Giant scorpion, like arthropods, crept quietly through the undergrowth, their armored bodies blending into the forest floor. Some possessed powerful pincers for grasping prey, while others relied on venomous stings to subdue the creatures they hunted. The entire ecosystem would have appeared almost otherworldly. The air hung heavy with moisture and oxygen. Strange buzzing sounds drifted through the forest as enormous insects passed overhead. Sunlight struggled to reach the ground through dense layers of towering plants. Beneath those shadows, giant invertebrates moved through soil and vegetation like silent guardians of a forgotten world. To modern eyes, these forests might seem like scenes from mythology rather than reality. Yet they were not fantasy. They were the natural outcome of a planet temporarily balanced in a unique way. High oxygen levels endless plant growth, and warm climates created conditions unlike anything seen before or since. But this strange world was also fragile. The very forests that filled the air with oxygen were quietly storing enormous amounts of carbon within their tissues and within the sediments beneath them. As plant material died and accumulated in swamps, much of it became buried beneath layers of mud and water. Over time, these buried forests would eventually become the coal deposits humans burn today. For millions of years, this system maintained a delicate balance between atmosphere, plants, and climate. But the planet itself never remains perfectly stable. Continents slowly drifted. Mountain ranges rose. Climate patterns shifted. Gradually, the conditions that supported these vast forests began changing. At first, the changes were subtle, but over time, something important began to break. And as the forests faltered, the strange world that had allowed insects to grow into giants would begin to disappear with them. For millions of years, the Carboniferous rainforests had ruled the continents. Vast wetlands stretched across the equatorial regions of the planet, dense with towering plants and tangled vegetation. Rivers wandered slowly through endless swamps where enormous trees rose above layers of mist and humid air. These forests did more than dominate the landscape. They shaped the entire atmosphere of the Earth. Through their constant growth and decay, they filled the air with oxygen and locked immense quantities of carbon deep within the ground. The strange world of giant insects and amphibian hunters had grown from this balance between land, air, and water. Yet the planet itself was never still. Beneath the forests, the continents drifted slowly across the globe. Over millions of years, tectonic forces pushed landmasses together and lifted mountain ranges into the sky. These changes altered the patterns of wind, rainfall, and temperature that had once sustained the great wetlands. Gradually, the climate began to shift. At first, the changes were subtle. Certain swamps became slightly drier during the warm seasons. Rivers that once flowed steadily began carving new paths across the landscape. Some forests that had stood for ages slowly thinned as moisture became less reliable. But as the centuries passed into millions of years, the transformation accelerated. The vast rainforest that once formed an unbroken belt across the continents began breaking apart. Instead of endless wetlands, the landscape became a patchwork of isolated swamps separated by drier regions. Some areas that had once supported towering plants slowly turned into open plains. The ancient forests were fragmenting. This fragmentation had profound consequences for the creatures that depended on them. The giant arthropods that ruled the forest floor and skies required humid environments to survive. Their large bodies depended on moist air and stable ecosystems filled with abundant plant life. As the forests shrank, these conditions became harder to find. At the same time, the atmospheric balance began changing, with fewer vast forests absorbing carbon and releasing oxygen. The concentration of oxygen in the atmosphere slowly declined. The air that had once allowed insects to grow to enormous sizes was gradually returning to more familiar levels. The giants began disappearing. Enormous dragonflies that once glided above the forests became rarer. The massive millipedes that crawled through thick layers of vegetation struggled as their environments vanished. Slowly, these creatures faded from the world they had once dominated. Amphibians faced an even greater challenge. Their entire biology depended on water, their skin required moisture, and their eggs could only develop in aquatic environments. As wetlands dried and swamps disappeared, the habitats they relied on grew increasingly scarce. Many amphibian species declined as the world around them changed. But not every creature was equally vulnerable to the shifting climate. Some animals had already evolved a remarkable advantage, one that now began reshaping the balance of life on land. The reptiles. With their protective skin and amniotic eggs, reptiles no longer depended on constant moisture or nearby water for reproduction. They could survive in drier environments, where amphibians struggled to endure. Their eggs could develop safely on land, allowing them to move farther from rivers and swamps. As the forests retreated and landscapes dried, reptiles found new opportunities. They spread across regions that amphibians could not reach. Dry forests, rocky plains, and expanding grasslands gradually became their territory. The changing climate that destroyed the ancient rainforest ecosystems created space for a different kind of life. What had begun as an environmental collapse was also the beginning of a new evolutionary race. The disappearance of the giant forests did not end life's expansion on land. Instead, it cleared the stage for creatures better suited to the planet's changing conditions. And among those creatures were reptiles whose descendants would eventually grow larger, faster, and more powerful than anything the ancient forests had ever known. The world was preparing for its next transformation. As the ancient Carboniferous rainforests fragmented and wetlands slowly retreated, the balance of life on land began to shift in ways few creatures could have anticipated. The humid environments that once sustained giant insects and amphibians were disappearing, replaced by landscapes that were drier, more open, and far less forgiving. For many species, these changes were devastating. But for reptiles, they were an opportunity. The features that had once seemed like small evolutionary advantages suddenly became the key to survival. Their skin, covered with protective scales, helped prevent the loss of moisture that plagued amphibians. While amphibians needed damp environments to keep their bodies from drying out, reptiles could move across dry ground with far greater freedom. Even more important was the secret hidden within their eggs. Because reptile eggs could develop safely on land, these animals no longer needed to return to water to reproduce. Rivers and swamps were no longer essential centers of life for them. A reptile could lay its eggs in soil, sand, or hidden nests beneath vegetation, leaving the next generation to develop safely inside protective shells. With this freedom came new possibilities. As climates changed and forests thinned, reptiles began spreading across landscapes that amphibians rarely reached. Dry woodlands, rocky uplands, and expanding plains slowly filled with small, adaptable reptiles exploring their surroundings. The continents were entering a new ecological era. For the first time in the history of vertebrate life, animals with backbones were no longer restricted to narrow belts of wet habitat. Entire regions far from rivers and swamps were becoming part of the living world. Across these environments, reptiles diversified into a wide range of forms. Some became quick, agile hunters that chased insects and smaller animals across the forest floor. Their sharp senses and flexible limbs allowed them to navigate dry terrain more efficiently than their amphibian predecessors. Others followed a different path. Instead of hunting prey, they fed on the growing vegetation that spread across drier forests and open plains. Plants adapted to the changing climate were expanding into new areas, providing fresh food sources for animals capable of digesting them. Predators and herbivores slowly formed the beginnings of new food webs across the land. Although these early reptiles represented a major step forward in the history of life, they were not yet the giants that would later dominate the planet. Most were small creatures often comparable in size to modern lizards. Their bodies were built for survival and adaptation rather than brute strength, but their importance lay not in their size. It lay in their independence. For hundreds of millions of years, vertebrate life had remained tied to water, even after limbs allowed animals to walk on land. Amphibians still needed rivers and swamps to reproduce. Their existence remained bound to moist environments. Reptiles broke the ancient dependency. They carried the tools needed to live their entire lives on dry ground. With scales protecting their bodies and amniotic eggs safeguarding their young, they could move across landscapes that earlier vertebrates could only briefly visit. The impact of this change spread across the continents. Valleys, plains, hillsides, and forests gradually filled with vertebrate life. Ecosystems that once contained only plants and invertebrates now included predators, herbivores, and scavengers with bones and muscles capable of navigating complex terrain. Life on land was no longer an experiment confined to swamps. It had become a permanent presence across the planet. Yet this was only the beginning of the reptile story. The early reptiles that spread across the changing landscapes were pioneers, but evolution rarely stops with its first designs. Within their descendants, new variations were already appearing. Subtle changes in posture, limb structure, and body shape. Over millions of years, these variations would lead to animals unlike anything the Earth had seen before, creatures that would dominate entire continents and reshape ecosystems on a global scale. because reptiles were only beginning their evolutionary journey, and soon some of their descendants would begin experimenting with entirely new body designs. Once reptiles gained the freedom to live entirely on land, evolution began exploring possibilities that had never existed before. The continents were no longer limited to narrow corridors of life surrounding water. Vast regions of forest, dry woodland, and open terrain now offered space for new forms of animals to emerge. With fewer environmental restrictions, reptile populations began spreading across these landscapes. As they expanded into different habitats, natural selection pushed their bodies in many directions at once. Some reptiles evolved longer limbs and more agile bodies, allowing them to move quickly across open ground. Speed became an advantage in environments where prey could escape or predators could approach from unexpected directions. These animals developed slender frames and flexible joints that allowed them to run rather than crawl. Others took a different path. In the thick vegetation of forests, stronger jaws became more important than speed. Certain reptiles developed powerful skulls equipped with sharp teeth, suited for seizing prey. Their eyes faced forward, improving depth perception and helping them judge distance when striking. These predators were among the first vertebrate hunters capable of dominating the land itself. Yet not all reptiles followed the path of carnivores. As plant life expanded across the continents, new food sources appeared in abundance. Some reptiles adapted to feed directly on vegetation, evolving broader teeth capable of grinding tough leaves and stems. Their digestive systems gradually adapted to process plant material, opening a completely different ecological role. These early herbivores became the foundation of growing terrestrial food chains. Predators hunted them, scavengers fed on their remains, and plants responded by evolving their own defenses. In this way, ecosystems across the continents began developing complexity that had never existed before. Over millions of years, reptile lineages diverged further and further from their shared ancestors. Some species remained small and agile, thriving in environments filled with insects and smaller animals. Others slowly grew larger as their bodies adapted to new diets and habitats. A few developed unique anatomical features that hinted at entirely new evolutionary directions. These changes were not coordinated or planned. Evolution simply experimented. Each variation that helped an animal survive was carried forward into the next generation. Small adjustments accumulated gradually, reshaping bodies and behaviors across enormous spans of time. When scientists look back at the fossil record today, these early reptiles appear almost like sketches in a larger design process. Within them lie the faint outlines of animals that would later dominate the Earth. Some of these reptile lineages would eventually give rise to turtles, whose protective shells would become one of the most recognizable adaptations in the animal kingdom. Others would lead to crocodile-like predators that ruled rivers and swamps with powerful jaws and armored bodies. Still others carried the evolutionary blueprints for creatures far more famous. Among these early reptile experiments were the distant ancestors of dinosaurs, and hidden within the dinosaur lineage itself would eventually appear birds, animals that took the reptilian body plan into the skies. Yet at this stage of Earth's history, none of those outcomes were visible. The reptiles spreading across the continents were not yet giants. They were not the towering creatures people imagine when they think of prehistoric life. Most were modest animals, testing new strategies for survival within environments that were themselves still changing. They were the early drafts of something much larger. Meanwhile, the planet beneath their feet continued to evolve as well. The continents were not fixed in place. Slowly, almost imperceptibly, enormous tectonic plates carried entire land masses across the surface of the Earth. Oceans opened and closed. Mountain ranges rose as plates collided. These geological movements would soon reshape climates, landscapes, and ecosystems across the globe. The reptiles experimenting with new forms were living on a planet that was quietly preparing for its next transformation. And when that transformation arrived, it would change the future of life on land in ways no creature could have predicted. Because while reptiles diversified across the continents, the Earth itself was rearranging the stage on which their story would unfold. And those slow geological shifts were about to trigger a dramatic new chapter in the history of life. While reptiles were slowly diversifying across forests, plains, and dry uplands, something far larger was unfolding beneath the surface of the planet. The continents themselves were moving. The ground beneath ancient forests and reptile-filled landscapes was not fixed in place. Enormous slabs of Earth's crust, tectonic plates, drifted slowly across the molten layers below them. Their movement was so gradual that no creature living on the surface could have sensed it. Yet over millions of years these slow shifts reshaped the entire geography of the world. Land masses that had once been separated by oceans began moving closer together. Shorelines changed, seas narrowed. Eventually continents collided. The collisions did not happen violently in a single moment. Instead, mountains rose slowly where land pushed against land. Oceans closed as their floors slipped beneath neighboring plates. Coastlines merged until what had once been separate continents became parts of a single enormous landmass. That landmass is known today as Pangaea. Stretching from pole to pole, Pangaea formed the largest continent the Earth had seen in hundreds of millions of years. Vast interior regions lay far from the moderating influence of oceans. The climates across these areas began changing in dramatic ways. Near the coasts, conditions remained relatively humid, where moist winds from the surrounding seas carried rain inland. But deep within the interior of the supercontinent, the story was very different. These regions became dry, harsh, and unpredictable. Without nearby oceans to supply steady moisture, rainfall became scarce. Vast deserts expanded across landscapes that once held forests. Temperatures swung dramatically between hot days and cold nights. Seasonal extremes grew more intense. For many forms of life, these conditions were difficult to endure. Amphibians, still dependent on water for reproduction and survival, found themselves increasingly restricted to the remaining wetlands and river valleys. Their ancient dominance of early terrestrial ecosystems continued fading as dry environments spread. But reptiles were well prepared for this new world. Their scaly skin helped conserve water in dry climates. Their amniotic eggs allowed them to reproduce without returning to ponds or rivers. Their bodies could withstand long journeys across landscapes where water might be scarce. Where amphibians struggled, reptiles thrived. Across the expanding deserts, dry forests, and open plains of Pangaea, reptiles began adapting to the changing environment. Some evolved stronger limbs and more efficient bodies capable of traveling long distances in search of food. Others developed specialized diets suited to new types of vegetation spreading across the dry landscapes. Predators emerged that hunted across open terrain rather than lurking near swamps. Plant-eating reptiles adapted to tougher, drought-resistant plants. Entire ecosystems began reorganizing themselves around the new realities of a drier planet. The scale of these changes was enormous. Instead of isolated environments scattered across separate continents, ecosystems now stretched across vast portions of a single supercontinent. Animals could migrate across enormous distances, spreading evolutionary innovations from one region to another. Competition intensified. Predators chased prey across endless plains. Herbivores adapted to new plant communities. Climate pressures forced animals to become more efficient, more resilient, and more specialized. Pangaea had become a powerful engine of evolution. The shifting climates, expanding deserts, and vast open habitats created new challenges that demanded new solutions. Animals that adapted survived and spread. Those that failed slowly disappeared. Among the reptiles responding to these pressures were lineages that would eventually give rise to some of the most remarkable animals in Earth's history. But for now, they remained small participants in a much larger transformation. The supercontinent had created a new stage, one unlike anything the planet had known before. Across its immense landscapes, evolution was quietly experimenting with forms that would one day grow larger, faster, and more powerful than any land animals that had come before. Their time had not yet arrived, but the conditions that would allow them to rise were already taking shape, because on the vast and changing landscapes of Pangaea, evolution was preparing its next great experiment. And soon, life on land would enter a completely new chapter. By the late Permian period, the continents of Earth no longer resembled the silent stone landscapes that had once stretched across the planet. Life had spread far beyond the narrow edges of rivers and wetlands. Across the enormous supercontinent of Pangaea, ecosystems flourished in astonishing variety. In some regions, forests still thrived where moisture gathered along river valleys and coastal plains. Towering plants formed dense canopies, casting long shadows across the ground where insects crawled through fallen leaves and early vertebrates hunted among tangled roots. Farther inland, the environment changed. Dry woodlands spread across vast stretches of land, where scattered vegetation clung to soil hardened by long seasons of heat. Beyond these areas lay open plains and deserts, where wind carved shifting patterns across the ground. Even in these harsher regions, life had adapted. The supercontinent had become a mosaic of environments. Across this immense landscape, reptiles had emerged as the dominant vertebrates. Their ability to live and reproduce far from water had allowed them to spread across regions that amphibians could rarely reach. But the reptiles of the Permian world looked nothing like the animals most people imagine when they hear the word. Some species resembled large, heavy-bodied lizards with sprawling limbs that carried them slowly across the ground. Others possessed massive skulls lined with powerful teeth, designed for crushing prey. Certain predators stalked the forests and dry plains, hunting smaller animals that ventured into open terrain. Alongside them lived plant-eating reptiles that wandered through woodland vegetation. These herbivores fed on tough leaves and stems, their teeth adapted for grinding the resilient plants that had evolved in the drier climates of Pangaea. Together, these animals formed complex ecosystems. Predators chased prey across dry valleys. Herbivores grazed on expanding plant life. Insects continued filling the air and soil, while amphibians remained near the scattered wetlands where water still shaped the landscape. For tens of millions of years, these communities thrived. Evolution refined their bodies and behaviors as species adapted to the seasonal climates of the supercontinent. Some animals developed stronger limbs to travel long distances in search of food. Others evolved new defenses against predators or specialized diets, suited to the changing plant life around them. The world appeared balanced. From a distant perspective, life on land had reached a stable and flourishing state. Food webs had grown intricate and resilient. Entire ecosystems seemed capable of enduring the shifting climates of the planet. But stability in nature can be deceptive. Deep beneath the surface of the earth, far below forests and plains, forces were gathering that no living creature could sense. Within the crust of the planet, enormous reservoirs of molten rock were beginning to stir. These volcanic systems had been quiet for ages, but the pressures building within them were immense. Eventually, they would awaken. When they did, the consequences would spread far beyond the landscapes of Pangaea. Gases trapped deep within the earth would rise into the atmosphere. The balance of air and climate that sustained life across the continents would begin to change. None of the animals roaming the forests or plains could see the danger approaching. Predators continued hunting across dry valleys. Herbivores wandered among scattered vegetation. Insects filled the air just as they had for countless generations before. Life moved forward, unaware that the planet itself was preparing something unprecedented. The catastrophe that was coming would not resemble the sudden disasters people often imagine. There would be no single moment when the sky split open, or the ground shattered beneath every living thing. Instead, the change would unfold slowly. The earth would begin altering the very air that animals breathed and the climates that shaped their survival. What followed was not a sudden explosion or impact from space. It was something far more gradual and far more devastating. The planet itself began poisoning its own atmosphere. Around 252 million years ago, the living world entered the darkest chapter in its long history. Scientists now call this event the Permian-Triassic extinction, but the name most often used is simpler and far more haunting: the Great Dying. It did not begin with a sudden impact from space or a single catastrophic explosion. Instead, it began deep beneath the surface of the Earth in a region that is now part of Siberia. There, enormous volcanic systems erupted with a force that continued not for days or years, but for hundreds of thousands of years. These eruptions were unlike the isolated volcanic events familiar today. Vast rivers of lava spread across immense regions of land, covering areas larger than many modern countries. But the lava itself was only part of the disaster. With every eruption, enormous quantities of gases were released into the atmosphere. Carbon dioxide poured into the air in staggering amounts. Methane, a powerful greenhouse gas, escaped from underground reservoirs. Toxic chemicals such as sulfur dioxide rose into the sky and spread across the globe. At first, the effects may have seemed subtle, but slowly, the atmosphere began changing. The rising concentration of greenhouse gases trapped more heat within the planet's climate system. Temperatures across the world began to climb. Seasons grew more extreme. Regions that had once supported stable ecosystems began experiencing conditions many species could not tolerate. On land, forests struggled to survive. As temperatures increased and rainfall patterns shifted, vegetation began dying in many regions. Without plant life to anchor soils and feed herbivores, food chains began unraveling. Meanwhile, the oceans were undergoing their own transformation. Warmer waters hold less dissolved oxygen, and as global temperatures rose, oxygen levels within the seas began falling. Large areas of the ocean became suffocating environments where marine animals could no longer survive. Some regions even developed toxic conditions, as certain bacteria released hydrogen sulfide gas into the water. The living world began collapsing. Species that had dominated the planet for millions of years suddenly found themselves unable to adapt quickly enough to the changing environment. Entire ecosystems disappeared as food sources vanished and climates shifted beyond the limits of survival. The numbers are difficult to imagine. Approximately 90% of marine species disappeared during this event. Coral reefs vanished from the oceans. Many groups of fish and invertebrates were wiped out entirely. On land, the losses were almost as severe. Nearly 70% of vertebrate species vanished. Forest ecosystems that had shaped the atmosphere for ages collapsed across vast regions. Animals that had thrived throughout the Permian period disappeared from the fossil record forever. The world grew quieter for a time. Landscapes that once supported complex communities of life became eerily empty. Rivers flowed through barren valleys. The skies held fewer insects. Predators that once roamed the plains were gone. It was the closest the planet has ever come to losing complex life altogether. Yet, even the most devastating extinction cannot erase life completely. Hidden among the ruins of collapsing ecosystems were small populations of animals capable of enduring the harsh new conditions. Some survived because they required little food. Others adapted quickly to extreme climates. A few simply endured long enough to see the worst of the crisis pass. Among those survivors were certain reptiles. They were not large or dominant creatures at the time. Most were small animals living quietly in the shadows of a devastated world. But they possessed characteristics that allowed them to endure where others could not. Their eggs could survive on land. Their bodies conserved water more efficiently than amphibians. Their adaptable diets allowed them to survive in environments where food had become scarce. While the Great Dying erased much of the ancient world, it also cleared the stage for something new. The ecosystems of the future would not resemble the ones that had vanished. And in the quiet aftermath of the greatest extinction the Earth had ever seen, a new group of animals began slowly rising. When the worst of the Great Dying had passed, the Earth was not the vibrant world it had once been. Landscapes that had supported forests, predators, and sprawling ecosystems were transformed into quieter and far more uncertain environments. In many regions, the ground lay bare where plants had once flourished. Rivers flowed through valleys that no longer echoed with the movements of large animals. Life had not disappeared entirely, but it had been reduced to scattered fragments. Across the supercontinent of Pangaea, the survivors were few and far between. Many ecosystems that once held intricate webs of species had collapsed into simple communities, struggling to persist. Food sources were limited. Climates remained unstable. Temperatures in some regions still rose to levels that made survival difficult. For a time, the planet seemed strangely empty, yet life has a remarkable ability to endure. Among the creatures that survived the catastrophe were animals that possessed one essential advantage: adaptability. They were not always the strongest or the most specialized species of their time. In many cases, they were the opposite. They were generalists. These animals could eat a wide variety of foods. They could survive in harsh conditions that eliminated more delicate species. They required fewer resources and could recover more quickly when environments changed. Many of these survivors were reptiles. Some were small omnivores that fed on whatever resources they could find, plants, insects, or carrion left behind by dying animals. Others were quick predators capable of chasing smaller prey across open ground. Their bodies allowed them to move efficiently through environments that had become hotter and drier than before. Compared with the dominant animals of the Permian world, these reptiles seemed unremarkable. Yet it was precisely their modest nature that allowed them to endure. Over time, as climate slowly stabilized and ecosystems began rebuilding, these survivors started spreading into the empty spaces left behind by extinct species. The process was slow. Forests took millions of years to recover in many regions. Plant life gradually returned to areas that had once become barren. With plants came herbivores. With herbivores came predators. Step by step, the living world began reconstructing itself. The descendants of the reptile survivors diversified as new opportunities appeared. Some adapted to hunt along rivers and wetlands where life was returning. Others roamed the expanding plains and dry forests, evolving new strategies for finding food and avoiding predators. The fossil record from this time shows a planet in recovery, where animals experimented with different forms and behaviors as ecosystems slowly regained complexity. Among these emerging reptiles was a group that would eventually become one of the most important lineages in Earth's history. They are known today as archosaurs. At first, archosaurs were small and easily overlooked animals, living among many other reptile species. Their bodies were lean and efficient, allowing them to move quickly across land. Their limbs began evolving toward a more upright posture that would later prove important for powerful movement. In the recovering ecosystems of the early Triassic world, they were simply one group among many. Nothing about them yet suggested the future that awaited their descendants, but evolution was already shaping the features that would later give archosaurs an advantage over many other reptiles. Their bodies were becoming more efficient at movement and breathing. Their skeletal structures were gradually adapting to support greater speed and endurance. These changes were subtle, unfolding across millions of years. The survivors of the Great Dying were rebuilding the world in small, patient steps. Forests returned. Food chains expanded. Life slowly filled the empty landscapes left behind by extinction. And among the many creatures participating in this recovery were the distant ancestors of animals that would one day dominate the entire planet. They were still small, still overshadowed by other reptile groups. But within their lineage lay the beginnings of something extraordinary. Among these quiet survivors were the earliest ancestors of a group that would soon reshape life on land, the dinosaurs. In the early Triassic period, the Earth was still a wounded planet. The Great Dying had erased vast ecosystems and left behind landscapes that felt strangely incomplete. Forests had not yet fully returned in many regions. Rivers cut through dry valleys where life struggled to regain its former richness. Across the enormous supercontinent of Pangaea, deserts spread across wide interior regions where rain rarely fell. The world was alive, but only barely. Insects crawled through scattered vegetation. Small reptiles hunted among rocks and dry woodlands. Ecosystems were rebuilding themselves piece by fragile piece, as if the planet was slowly remembering how life was meant to function. It was within this uncertain world that a new group of reptiles began quietly spreading across the continents. These animals belonged to a lineage that scientists now call archosaurs. Their descendants would one day include crocodiles, flying pterosaurs, and the dinosaurs themselves. But in the early Triassic, archosaurs were simply one of many reptile groups trying to survive in a harsh and competitive environment. Most of them were modest creatures. Some moved on four legs, creeping cautiously across the ground, much like other reptiles of their time. Others experimented with slightly different body structures, with limbs that positioned themselves more directly beneath the body instead of sprawling out to the sides. This subtle difference would eventually prove important. An upright posture allowed an animal to move with greater efficiency. Instead of dragging its body across the ground, it could lift itself higher and travel with more energy and speed. In the wide landscapes of Pangaea, where food might lie far from shelter. This advantage mattered. Among the many archosaurs exploring these new body designs, one lineage began developing features that set it apart. Their hind limbs grew longer and stronger. Their bodies balanced differently, allowing them to move with surprising agility. Instead of relying equally on all four legs, these animals increasingly shifted their weight toward their back limbs. This posture allowed them to run. Speed became their strength. These small archosaurs could cross open ground quickly, chase prey, or escape predators with bursts of motion that many other reptiles could not match. Their bodies were built not for brute force but for efficiency and endurance. These were the earliest dinosaurs. To modernize, the word dinosaur often brings to mind towering giants that shook the ground with every step. But the first dinosaurs were nothing like that image. Most were small animals, some no larger than modern birds or dogs. They moved quickly through recovering ecosystems, weaving between patches of vegetation and across dry plains where the scars of the great dying still lingered. Their world was far from stable. Many reptile groups competed for the same resources. Food remained scarce in certain regions. Climate conditions across Pangaea could be extreme, with long dry seasons and sudden storms that reshaped landscapes overnight. In such an environment, survival favored animals that could move efficiently and adapt quickly. The earliest dinosaurs possessed exactly those qualities. Their long legs allowed them to travel across large territories in search of food. Their lighter bodies required less energy than the heavier reptiles that had once dominated the Permian world. Their upright posture gave them stamina that sprawling reptiles struggled to match. These advantages did not make them rulers of the planet, not yet. At this stage in Earth's history, dinosaurs were still minor participants in the ecosystems of the Triassic world. Larger reptile groups still occupied many dominant roles. Dinosaurs lived alongside them, hunting smaller animals or scavenging where they could. But within their bodies lay a design that would prove remarkably powerful over time. Their speed, balance, and efficient movement gave them abilities that many other reptiles lacked. As ecosystems continued rebuilding and competition intensified, those advantages would slowly begin to matter more and more. The first dinosaurs were not giants. They were small runners in a recovering world, evolving quietly in the shadows of other creatures. Yet hidden within their anatomy was a combination of traits that would eventually reshape life on land. And soon, something about these early dinosaurs would give them a powerful advantage over many of their reptile competitors. At first glance, the early dinosaurs of the Triassic world did not appear especially remarkable. They were not the largest reptiles, nor were they the most heavily armored, in a landscape already filled with strange and powerful animals. These small runners could easily have gone unnoticed, yet something about their bodies was quietly different. Most reptiles of the time moved with limbs that sprawled outward from their sides. This posture worked well for short bursts of movement, but it required significant energy. Each step forced the animal to swing its body from side to side, making long-distance travel exhausting. Dinosaurs followed a different design. Their legs extended downward beneath their bodies rather than outward. This upright posture allowed their weight to rest directly over their limbs, creating a more balanced and efficient form of movement. Instead of dragging themselves across the ground, dinosaurs could move forward with smoother strides. The difference may seem small, but in nature small advantages can reshape entire ecosystems. Animals with upright limbs could run longer distances without tiring quickly. Their movements required less energy, allowing them to travel farther in search of food or escape predators more easily. Their bodies could support faster bursts of speed when necessary. Even their breathing systems functioned more effectively during movement. When animals move with a sprawling posture, the motion of their limbs compresses the chest, interfering with breathing. An upright posture reduces this problem, allowing oxygen to flow more freely while the animal runs. In environments where survival often depended on endurance, this advantage mattered greatly. The early dinosaurs were built for efficiency. In the unpredictable landscapes of the Triassic world where food resources could be scattered and competition remained intense, efficiency was everything. Animals capable of moving farther and faster often had a better chance of surviving. Over time, these advantages allowed dinosaurs to expand into new ecological roles. Some species evolved into agile predators. Their speed and balance allowed them to pursue smaller animals across open terrain or through sparse vegetation. Their jaws and teeth adapted for grasping and tearing prey, making them effective hunters within the recovering ecosystems. Other dinosaurs followed a different path. Certain lineages evolved into plant eaters, feeding on the vegetation that slowly returned as the world recovered from the Great Dying. Their bodies adapted for processing leaves, stems, and other plant material that spread across the expanding forests and plains. With predators and herbivores appearing among their ranks, dinosaurs began occupying multiple positions within food webs. At first their presence remained limited. Other reptile groups still dominated many ecosystems. Large predators unrelated to dinosaurs hunted across the plains, and several reptile lineages competed for similar resources. But as millions of years passed, the balance began shifting. The efficient body design of dinosaurs allowed them to adapt more easily to changing environments. They could move across wider territories and exploit food sources that were harder for other reptiles to reach. Slowly, their populations increased. Meanwhile, some competing reptile groups struggled to keep pace with the changing conditions of the Triassic world. Little by little, dinosaurs became more common across the continents. The transformation was gradual, unfolding across vast stretches of time. No single moment marked the rise of dinosaur dominance. Instead, the shift occurred quietly as their evolutionary advantages accumulated generation after generation. The truth is that dinosaurs did not dominate the Earth because they were initially the biggest or the most fearsome animals alive. They succeeded because their bodies were designed differently. Their upright posture, efficient movement, and endurance allowed them to thrive in environments where others faltered. These qualities gave them the flexibility to survive and adapt as climates shifted and ecosystems continued evolving. Still, even with these advantages, dinosaurs did not immediately take control of the planet. Other reptile groups remained powerful competitors. The Triassic world was still crowded with animals experimenting with different evolutionary strategies. But the planet itself was not finished reshaping the balance of life. Before dinosaurs could fully rise to dominance, another global catastrophe would intervene. And when that event arrived, it would remove many of the rivals standing in their way. For tens of millions of years after the first dinosaurs appeared, they lived in a world crowded with rivals. The Triassic landscapes of Pangaea were filled with many reptile groups experimenting with different body designs and survival strategies. Some of these creatures were larger and more powerful than the early dinosaurs. Others occupied similar roles as hunters or plant eaters, competing for the same food and territory. Dinosaurs were spreading gradually, but they were not yet the dominant animals of the planet. Across forests, deserts, and floodplains, other reptiles still ruled many ecosystems. Massive predators stalked prey along riverbanks. Armored herbivores grazed across plains. Strange crocodile-like animals walked upright on long legs and competed with dinosaurs in both speed and strength. For a long time, the balance of power remained uncertain. Dinosaurs were successful, but they were only one group among many. Then, around 201 million years ago, the planet changed again. The cause lay deep beneath the surface of the Earth, where enormous geological forces were reshaping the supercontinent itself. Pangaea, which had once formed a single immense landmass, was beginning to break apart. As the continents slowly pulled away from one another, vast cracks opened in the crust. From those cracks, volcanoes erupted on an unimaginable scale. These eruptions were not isolated mountains, releasing occasional flows of lava. Instead, entire regions of the Earth's crust split open, pouring molten rock across enormous distances. Lava spread over landscapes in layers hundreds of meters thick, covering vast areas of the planet. With the lava came enormous quantities of gas. Carbon dioxide surged into the atmosphere in immense volumes. Other greenhouse gases followed, trapping heat within the climate system. Temperatures rose quickly compared with the slow evolutionary pace of most species. The world began warming once again. Climates shifted rapidly across the continents. Some regions experienced intense heat and drought, while others faced violent storms and unstable seasons. Plants struggled to adapt to the changing conditions, As vegetation changed, food chains across the land began unraveling. The oceans were affected as well. Rising temperatures altered currents and reduced oxygen levels in certain regions, placing additional stress on marine life. The result was another global extinction. It was not as devastating as the Great Dying that had occurred millions of years earlier, but it was severe enough to reshape ecosystems across the planet. Many large reptile groups that had competed with dinosaurs vanished from the fossil record during this time. Predators that once dominated the plains disappeared. Herbivores that had grazed across ancient forests vanished as well. Once again, the balance of life shifted, and once again the survivors would inherit the world that remained. Among those survivors were the dinosaurs. Their efficient bodies, adaptable diets, and ability to thrive across different environments allowed them to endure the changing climate better than many of their competitors. When the extinction ended and ecosystems began rebuilding, dinosaurs found themselves in a dramatically altered world. Many of their rivals were gone. The landscapes of the early Jurassic period offered vast ecological opportunities waiting to be filled. Dinosaurs began spreading rapidly across the continents, evolving into new species that occupied nearly every role within terrestrial ecosystems. Some lineages grew larger, developing massive bodies capable of browsing vegetation high above the ground. Others became powerful predators that hunted across plains and forests. Over time, dinosaurs became the dominant animals of the land. For the next 160 million years, their descendants would shape the ecosystems of the Earth more than any other creatures. Forests, deserts, and floodplains across the continents would become the domain of dinosaurs in forms both enormous and small. Yet their rise did not begin with overwhelming strength. It began quietly, with small runners moving through recovering landscapes while the world around them changed. Chance, climate, and catastrophe cleared the path ahead. And before long, the age of dinosaurs had truly begun. But even the reign of giants would not last forever, because the story of life on land still held many unexpected twists waiting in the future. For more than 160 million years, the continents of Earth belonged to dinosaurs. Across the vast landscapes of the Mesozoic world, their presence shaped nearly every ecosystem on land. Forests, plains, river valleys, and coastal wetlands all carried the marks of their movements. In some regions, enormous plant-eating dinosaurs wandered slowly across floodplains, their massive bodies towering above the vegetation. Long necks stretched upward to reach leaves high within ancient trees. Herds of these giants traveled together, leaving deep footprints in soft ground as they moved through forests and open landscapes. These animals were larger than any land creatures alive today. Their immense size was not simply a curiosity of evolution. It was part of a balance that had developed across millions of years. Massive herbivores consumed vast amounts of vegetation, shaping forests and grasslands with their feeding habits. In turn, predators evolved to hunt them. Among these hunters were dinosaurs built for speed and precision. Some species possessed long, powerful legs that allowed them to pursue prey across open terrain. Their bodies were light and agile, perfectly suited for chasing smaller dinosaurs that tried to escape across plains and riverbanks. Other predators relied on stealth instead of speed. They moved quietly through dense vegetation, waiting for the moment when an unsuspecting animal wandered too close. The balance between hunter and hunted filled the continents with life and movement. Dinosaurs were not the only remarkable creatures of this age. Above the forests and coastlines, the skies belonged to flying reptiles known as pterosaurs. Their wings carried them across oceans, and inland valleys where they searched for fish or small animals far below. Meanwhile, the seas were ruled by entirely different reptiles. Massive marine predators cruised through ancient oceans, hunting fish and squid in waters that covered large portions of the planet. Some had bodies shaped like enormous dolphins, built for speed in the open sea. Others possessed long necks or massive jaws designed to capture prey in deep water. Together, these animals formed a world that seemed stable and powerful. To an observer standing on the surface of the Earth during this era, it would have been almost impossible to imagine the planet without dinosaurs. They dominated the food chains of land ecosystems. Their descendants spread across every continent, Their presence shaped forests, plains, and rivers in ways that influenced every other species around them. They were not simply inhabitants of the world, they were its rulers. For millions upon millions of years, their reign continued uninterrupted. Entire generations of plants, insects, and smaller animals evolved alongside them, adapting to environments where dinosaurs were always present. Life had settled into a rhythm. The seasons changed. Rivers flooded and receded. Forests grew and fell. Through it all, dinosaurs thrived across the continents, appearing as permanent and unshakable as the mountains themselves. Yet the planet has never truly been stable. Beneath the steady patterns of life, forces beyond the control of any creature were always shaping the future. Deep within the Earth, tectonic movements slowly altered the geography of continents. In the atmosphere, climate shifted in subtle ways that unfolded across long stretches of time. And beyond the atmosphere, far beyond the reach of any living thing, another force had already begun moving toward the Earth. Somewhere in the darkness of space, an object drifted silently through the solar system. For millions of years it traveled unnoticed, following a path that would eventually intersect with the orbit of our planet. The dinosaurs that ruled the Earth could not see it. They continued living within their ancient world of forests, plains, and oceans, unaware that the balance sustaining their dominance was about to end. Because what happened next would not unfold slowly over millions of years. It would happen in a single moment. Approximately 66 million years ago, the long reign of the dinosaurs ended with an event so violent that its effects reshaped the entire planet. The cause was not a slow environmental shift or gradual evolutionary change. It was a collision. A massive asteroid, roughly 10 kilometers wide, was traveling through space when its path intersected with Earth's orbit. Moving at extraordinary speed, the object plunged toward the surface of the planet and struck near what is now the Yucatan Peninsula in modern-day Mexico. The moment of impact released energy beyond ordinary comprehension. The explosion has been compared to billions of nuclear weapons detonating at once. In an instant, the asteroid slammed into the shallow seas that once covered that region, excavating a crater more than 180 kilometers wide. The surrounding rock vaporized. A column of molten debris blasted high into the atmosphere. Shock waves rippled outward across the planet. Earthquakes shook continents thousands of kilometers away. Massive tsunamis surged through ancient oceans, crashing into coastlines with unimaginable force. Entire ecosystems near the impact zone vanished within moments, but the immediate destruction, devastating as it was, did not end the catastrophe. The asteroid impact hurled enormous quantities of dust, ash, and vaporized rock high into the atmosphere. This material spread across the globe, forming a thick veil that blocked sunlight from reaching the surface of the Earth. The skies darkened. For months, and perhaps even years, sunlight struggled to penetrate the cloud of debris encircling the planet. Temperatures dropped as the sun's warmth was partially shut out. Plants, which depended on sunlight for photosynthesis, began to fail. Forests withered. Vegetation across continents stopped growing, and in many regions it died entirely. The collapse of plant life struck at the very foundation of the food chain. Herbivores that relied on vegetation soon found themselves without sufficient food. As plant-eating animals weakened and disappeared, the predators that hunted them faced starvation as well. The balance that had sustained ecosystems for millions of years unraveled rapidly. In the oceans, similar changes unfolded. Plankton, tiny organisms that form the base of marine food webs, declined as sunlight vanished from the upper layers of the sea. Without plankton, larger marine animals lost their primary food source. Across land and sea, life entered a sudden and brutal crisis. Within a relatively short span of geological time, nearly 3/4 of all species on Earth disappeared. Entire groups of animals vanished from the fossil record, leaving behind only fragments of the ecosystems that had once thrived during the age of dinosaurs. Among the victims were the non-avian dinosaurs themselves. For more than 160 million years they had dominated life on land. Their descendants had spread across continents, filling ecological roles as predators, herbivores, and scavengers. They had survived shifting climates, changing continents, and countless generations of evolution. Yet they could not survive the aftermath of the asteroid impact. The ecosystems that supported them collapsed too quickly. Without stable plant life and functioning food chains, even the most powerful animals could not endure. The age of dinosaurs came to an end. Their disappearance marked one of the most dramatic turning points in the history of life. Creatures that once seemed permanent rulers of the Earth vanished, leaving the continents strangely quiet. Once again, yet extinction, even on this immense scale, never erases life completely. Hidden within burrows, forests, and sheltered environments were small animals that survived the catastrophe. These creatures had lived quietly in the shadows of the dinosaurs for millions of years. They were not giants, they were small, adaptable, and capable of enduring the harsh conditions that followed the impact. And from these survivors, the next chapter of life on land would begin. Long before the asteroid struck the Earth, small mammals had already been living quietly among the giants of the dinosaur world. They were not dominant animals, nor were they particularly noticeable in the ecosystems that surrounded them. In a world where enormous reptiles ruled forests, plains, and river valleys, mammals existed mostly in the background. Most of them were small creatures. Many were no larger than a modern mouse or shrew. Their lives were spent moving carefully through undergrowth, climbing through branches, or burrowing beneath the soil. During the daytime hours, when dinosaur predators were most active, these animals often remained hidden. Night became their refuge. Over millions of years living alongside dinosaurs shaped the biology of early mammals in remarkable ways. Many evolved sharp hearing and sensitive noses that helped them navigate in darkness. Their bodies developed fur that trapped heat, allowing them to remain active during cooler nighttime temperatures. Perhaps most important of all, they possessed warm-blooded metabolisms. Unlike many reptiles which rely heavily on external warmth from the sun, mammals could generate their own body heat. This ability allowed them to remain active even when temperatures dropped or sunlight disappeared. These traits had originally evolved as survival strategies in a dangerous world filled with reptilian predators. But when the asteroid struck the Earth 66 million years ago, those same adaptations suddenly became powerful advantages. The aftermath of the impact created a planet unlike the one dinosaurs had dominated for so long. Sunlight was blocked by clouds of dust and debris that lingered in the atmosphere. Temperatures dropped as the sunlight faded. Plant life struggled to survive in the dim, cooler world that followed. Large animals suffered the most. Creatures with enormous bodies required vast amounts of food to survive. When plants died and herbivores vanished, the predators that depended on them soon followed. The ecosystems that had once supported massive dinosaurs collapsed rapidly. Small mammals faced a different reality. Because their bodies were small, they required far less food to survive. Insect seeds and small fragments of plant material could sustain them when larger animals starved. Many mammals already lived in burrows or sheltered environments where they could escape harsh conditions above ground. These hiding places became lifelines during the dark years after the asteroid impact. Protected beneath the soil or hidden within crevices, small mammals endured while the surface world changed dramatically. Their ability to remain active in cooler temperatures also helped them survive in the dim climate created by the dust-filled atmosphere. Slowly, the skies began clearing. Sunlight returned to the planet. Plants began growing again across recovering landscapes. Rivers flowed through forests that slowly reappeared after years of environmental devastation. But the world that emerged from this catastrophe was very different from the one that had existed before. The dinosaurs were gone. The enormous predators and herbivores that once dominated land ecosystems had vanished, leaving vast ecological spaces empty. Food sources that had once been tightly controlled by large reptiles were suddenly available. For the first time in millions of years, mammals found themselves living in a world with far fewer large competitors. Opportunity appeared everywhere. Some mammals began growing larger as food supplies increased. Others adapted to new diets or environments that had once been inaccessible. Certain species took to the trees while others spread. across plains and forests that had once belonged to dinosaurs. The small animals that had once hidden in darkness were beginning to explore a much larger world. Their rise would not happen overnight. Millions of years would pass before mammals truly dominated life on land. But the foundation of that future had already been laid. The creatures that would eventually inherit the Earth had once been tiny animals hiding from dinosaurs in the dark. Now, with the ancient rulers gone, the path ahead was open, and as the planet recovered from the asteroid impact, mammals began spreading into ecological roles that had once belonged to dinosaurs. The story of life on land was entering an entirely new era. When the dinosaurs vanished from the Earth, the planet did not remain empty for long. Ecosystems that had once been dominated by giant reptiles suddenly contained vast spaces waiting to be filled. Forests returned to landscapes that had slowly recovered from the aftermath of the asteroid impact. Rivers once again flowed through valleys, rich with plant life. But the animals walking these lands were no longer dinosaurs. The survivors of the catastrophe were mostly small creatures, adaptable, resourceful, and capable of surviving difficult conditions. Among them were mammals, animals that had once lived quietly in the shadows of larger reptiles. Now those shadows were gone. With the disappearance of the dominant dinosaurs, mammals began spreading into ecological roles that had been inaccessible for millions of years. Environments that once belonged to giant herbivores and massive predators were suddenly open. Evolution responded quickly. Over time, mammals diversified into an extraordinary range of forms. Some species grew larger as they adapted to grazing on vegetation that spread across forests and plains. Others evolved into hunters capable of chasing prey across open landscapes. Each new environment presented opportunities, and mammals proved remarkably capable of adapting to them. Their rise was gradual but steady. Across continents that were slowly drifting into new positions, mammals expanded into forests, mountains, plains, and coastal regions. Their bodies evolved in many different directions as natural selection shaped them to fit their surroundings. Some mammals followed an unexpected path and returned to the oceans. Over millions of years, certain lineages adapted to life in water so completely that their bodies transformed into streamlined swimmers. Their limbs evolved into flippers, their nostrils shifted upward to become blowholes, and their bodies grew massive once again. These animals would eventually become whales and dolphins. Other mammals explored the skies. From small, tree-dwelling ancestors emerged creatures capable of powered flight. Their forelimbs stretched into wings, supported by delicate membranes of skin. With this adaptation, mammals joined birds as animals that could move freely through the air. These were the first bats. Meanwhile, countless other mammals spread across land ecosystems. Herds of grazing animals wandered through expanding grasslands. Predators evolved sharp teeth and powerful limbs to hunt them. Burrowing mammals shaped the soil beneath forests and plains, while tree-dwelling species moved among branches in dense woodlands. Life on land had entered a new era of diversity. As climates shifted and continents slowly rearranged themselves, mammals continued adapting to new conditions. Their ability to regulate body temperature, nurture their young, and learn complex behaviors gave them advantages in many environments. Among the many mammals living in ancient forests were small primates. These animals were not yet anything like humans. They were small creatures that lived in trees, moving carefully among branches in search of fruit, insects, and leaves. Their bodies possessed features that helped them navigate this complex environment. They had grasping hands capable of holding onto branches. Their eyes faced forward, providing depth perception that allowed them to judge distances while climbing or leaping. Their brains were slightly larger and more flexible than those of many other mammals. These traits helped them survive in forest habitats where agility and awareness were essential. At the time, however, these primates were simply one branch of a rapidly expanding mammalian family tree. They lived alongside many other species, each adapting in its own way to the recovering ecosystems of the planet. Nothing about them yet suggested the future that lay ahead. They were small animals in vast forests, one evolutionary experiment among countless others unfolding across the continents. Yet evolution often hides its most important possibilities within ordinary beginnings. Among these early mammals, one lineage would eventually begin developing abilities that would reshape the story of life on Earth in ways no creature had ever done before, and that lineage had already begun its quiet journey. Over the course of millions of years, the small primates that once moved quietly through ancient forests continued evolving in subtle but profound ways. Their early advantages, grasping hands, forward-facing eyes, and flexible bodies, had helped them survive among branches and dense vegetation. But evolution was beginning to shape something even more powerful within them. Their brains were slowly growing larger. At first, the changes were modest. Slight increases in brain size allowed these animals to remember the locations of food, recognize members of their group, and navigate the complex environments of forest canopies. Life in these habitats demanded constant awareness. One misstep could mean falling from great heights, while a moment of inattention might attract the notice of a predator. Memory and quick decision-making became valuable traits. Over time, these primates also began living in increasingly complex social groups. Cooperation offered safety in numbers, but it also introduced new challenges. Individuals needed to recognize allies, remember past interactions, and respond to the shifting relationships within their communities. These pressures encouraged the development of more sophisticated behavior. Communication signals became more varied. Gestures, vocal sounds, and facial expressions allowed individuals to share information or warn others of danger. Within these groups, young animals learned behaviors by watching older members, gradually acquiring knowledge that helped them survive. In this way, intelligence itself began becoming an evolutionary strategy. Across millions of years, certain primate lineages continued developing larger brains relative to their body size. Their hands became more dexterous, capable of manipulating objects with increasing precision. Their eyes, positioned toward the front of their faces, provided depth perception that helped them judge distance and movement. Eventually, some of these primates began spending more time on the ground. Moving across open terrain presented new challenges but also new opportunities. Standing upright for brief moments allowed individuals to see over tall grass or carry objects in their hands. Gradually, certain lineages began adopting a more upright posture for longer periods. With hands freed from the constant task of walking, those hands could begin doing something else. They could grasp, they could shape, they could build. Over immense spans of time, the descendants of these primates developed increasingly refined control over their fingers and thumbs. Tools began appearing in the archaeological record, simple stones, shaped for cutting or pounding. These tools allowed early humans to access new food sources and defend themselves against predators. As tools improved, brains continued expanding. Language slowly emerged, allowing information to pass between individuals in ways that had never existed before. Knowledge no longer had to disappear when one generation died. Instead, it could be shared, preserved, and improved. Culture was born. With culture came the ability to adapt to environments in ways no other species could. Humans no longer relied solely on physical evolution to survive new conditions. They could change their behavior, create shelters, develop clothing, and eventually cultivate food. Within a remarkably short span of geological time, humans spread across nearly every continent on the planet. Forests, plains, deserts, and mountains all became part of their world. Small communities gradually grew into villages, and villages into cities. Agriculture transformed landscapes as humans learned to cultivate plants and domesticate animals. Technology advanced with astonishing speed. Tools of stone gave way to metals. Knowledge accumulated through writing and shared learning. Machines, engines, and digital networks appeared within only a few thousand years, an instant when viewed against the immense timeline of life on Earth. Yet despite this complexity, the human story remains deeply connected to the same evolutionary journey that began hundreds of millions of years earlier. The creatures that once crawled from ancient oceans had slowly transformed across countless generations. Fish exploring shallow waters became amphibians. Reptiles spread across dry continents. Mammals survived catastrophe and diversified into countless forms, and among them, one lineage eventually developed the ability to reflect upon its own existence. The creatures that once struggled simply to survive in hostile environments had become beings capable of understanding their origins. to see the long path that led from the first steps onto land to the modern world, and to ask questions about where that journey might lead next. But to truly understand the meaning of this story, it helps to return to where it all began. When the immense history of life on Earth is viewed across the vast scale of geological time, the entire story of animals living on land can be traced back to a beginning that was almost fragile. Hundreds of millions of years ago, the continents were empty places, wind swept across bare rock, rain carved valleys through silent landscapes. The oceans contained thriving ecosystems, but the land itself remained largely untouched by animal life. It was a quiet world waiting for something to change. Then, along muddy shorelines and shallow coastal waters, small creatures began exploring the boundary between two worlds. They were not designed for land. Their bodies still belonged to the ocean. Their limbs were awkward, their breathing imperfect, their movements uncertain. When they pulled themselves across wet sand or crawled through tidal flats, they did so as experiments in survival, rather than confident pioneers. Yet those first awkward steps mattered more than anyone could have imagined. Each moment a creature survived outside the water, evolution learned something new. Over generations, bodies slowly changed. Fins strengthened into limbs. Lungs improved. Skin adapted to resist drying air. The shoreline became a gateway. From that gateway emerged the long story of life on land. Plants spread across the continents, turning barren ground into green landscapes. Arthropods followed, crawling across the first soils and building the earliest terrestrial ecosystems. Vertebrates eventually joined them, stepping cautiously from the water to explore forests, swamps, and open plains. Over millions of years, the complexity of life expanded. Towering forests filled the air with oxygen. Giant insects ruled humid environments. Beneath dense vegetation, reptiles spread across deserts and dry plains as continents merged into vast supercontinents. Later came the age of dinosaurs, when enormous creatures walked across landscapes that stretched for thousands of kilometers. For over 160 million years, they dominated life on land, shaping ecosystems across the entire planet. Even their disappearance did not end the story. Small mammals survived the catastrophe that ended the age of dinosaurs. From those quiet survivors came a new wave of life spreading across forests, oceans, and skies. Among them were primates whose descendants would eventually evolve intelligence, language, and technology. Humans appeared only in the final moments of this immense timeline. Yet the cities, civilizations, and questions of modern humanity remain connected to that same ancient journey. The forests surrounding us, the animals that share our planet, and even the ground beneath our feet are part of a story that began when life first ventured beyond the sea. Every creature walking across land today carries that legacy. Birds flying above forests trace their ancestry back through dinosaurs to those early reptiles. Mammals running across plains descend from the small survivors that lived in the shadows of giant predators. Reptiles basking in the sun reflect evolutionary paths that began when animals first learned to survive away from water, and humans themselves are part of the same lineage. Every step a person takes across the ground echoes a much older moment in Earth's history, a moment when a strange animal lifted its body from shallow water and crawled onto land for the first time. Those early pioneers did not know they were beginning one of the most important transformations in the history of life. They were simply surviving, searching for food, escaping danger, adapting to unfamiliar conditions. But evolution carried their legacy forward. The silent continents that were once barren stone landscapes are now filled with forests, animals, and civilizations. Life on land has grown into something astonishingly complex, shaped by hundreds of millions of years of adaptation and change. Yet the journey that began with those first uncertain steps has never truly ended. It continues with every generation of life that walks across the earth today,